Alright guys, let's continue acceleration. Solve this problem. Wow, great job. There were two ways to solve it. Did you use the definition of acceleration, finding acceleration, and then plugging in the formula? Or did you use average velocity? Both ways give the same answer, which is true in a lot of physics problems. There's more than one way to solve it. They'll give you the same answer as long as they're both correct. And you can use that to check your answers. Okay, so acceleration is really important. We're going to learn a new way to use the equations from last unit to solve a new kind of problem. So check out this video really fast.
Eventually, she came across an experiment performed by a Dutch scientist, Willem Schravesand, that would prove her point.
Schravesand in Leiden has been dropping lead balls into a pan of clay.
Dropping lead balls into clay, how very imaginative.
Using Newton's formulas, Monsieur Voltaire, he then drops a second ball from a higher height, calculated to exactly double the speed of the first ball on impact. So, monsieur, care for a little wager? Newton tells us that by doubling the speed of the ball, we will double the distance it travels into the clay. Leibniz asks us to square that speed. If he is correct, the ball will travel not 2, but 4 times as far. So, who is correct?
Okay, so in case you guys didn't catch all that, really straightforward. They drop a ball into clay at a certain speed, and the ball goes a certain distance into the clay, makes a certain size dent. If the ball is going twice as fast, will it make 2 times the dent, 4 times the dent, or some other kind of dent? What do you guys think? I'll ask my babies too. Hey babies, what do you think? Will the ball go twice as far, 4 times as far, or some other thing? I don't know. Daisy, what do you think? The ball was going twice as fast, so it'll go twice as far. Twice as far. Hazel, what do you think? The woman in the video said 4 times, so 4 times. That's not really an answer. Okay. Sage, what do you think? Huh? Oh, I was asleep. Sorry, Mr. Lamb. Okay, well, as long as you guys tell me what you think, I can hear all your fascinating answers. And then we'll watch the video.
Monsieur, I feel Mr. Newton's reputation dwindling ever so slightly.
Oh, mon père, Tweed, do not succumb to her. There is no earthly reason to ascribe hidden forces to this Dutchman's lead balls.
Well, the ball travels 4 times further.
Turns out, Leibniz is the one who was right. It's the best way to express the energy of a moving object. If you drive a car at 20 miles an hour, it takes a certain distance to stop if you slam on the brakes. If you're going 3 times as fast, you're going 60 miles an hour, it won't take you 3 times as long to stop. It'll take you 9 times as long to stop.
Oh, well, it does seem worth consideration.
Perhaps we might look over his calculations.
I have already checked his figures. I am sure Leibniz is correct on this point. I intend to include a section on this matter in my book.
Okay, so it turns out if your lead ball hits the clay twice as fast, it won't make twice the dent. It'll make 4 times the dent. You guys want to learn why? Well, here we go. So let's write the formulas, and then we'll think about this. So the formulas we learned last lesson are V equals V naught plus AT, and D equals V naught T plus 1/2 AT squared. So the assumption we're going to make about the clay is that the clay gives the ball the same acceleration. Technically it's deceleration because it's slowing the lead ball down. So look at the second formula. We're trying to find D, And it doesn't make sense. How come the ball doesn't go twice as far? We think if you double the speed it hits the clay, you double the initial velocity, it should double the displacement into the clay. The dent thickness is d, the displacement of the ball, while it's slowing down. So if A is the same and V naught is doubled, how come D isn't doubled? Do you guys see the answer? My babies see the answer. Tell me if you see the answer. How come doubling V naught doesn't double D if A is the same? Sage, you figured it out? Tell them. I'm going to point with my head because my head is great. V naught is doubled, but T is also doubled. You have double V naught because the ball hits at twice the speed. But look at the first formula. If you double V naught and have the same acceleration, it'll take twice the time to get down to the right V. What's the V? Not V naught. What's V? V, when the ball makes a dent, it stops. So V is 0. The ball goes from some initial velocity to a velocity of 0. If you double V naught and have the same A, you need double the T. So V naught gets doubled, T gets doubled, D gets quadrupled. It takes 4 times the distance to stop the ball in the clay. Wow, good job, babies. And good job, you guys, to figure it out too. And good job to that French lady in that video. She was pretty smart. So, not just V naught affects D. You also have to think about T. Not only does the ball take twice, no, not only is the ball going twice as fast, it's moving for twice as long. Because since it was going twice as fast, it takes more time to stop. So it was going twice as fast for twice as long, therefore it went 4 times the distance into the clay and made 4 times the dent. Good job, us. We did it. We are physics scholars right here. I'm going to do some fancy stuff right now. This is just algebra, fancy algebra. Just trying to flex my math skills on you kids. Ready, set, here it goes. Where's there no glare? Like right here? That's fine. Okay, so we know the assumption that we proved wrong, lesson 3. We're going to assume it's correct, because it is correct if acceleration is constant. D over T and V plus V naught over 2 are both formulas for average velocity. But I don't care about average velocity. I'm just going to set them equal to each other. Since they both equal average velocity, they must equal each other too. A very similar looking formula, but not the same, we saw in the definition of acceleration. Acceleration is V minus V naught over T, not over 2 over T. Similar formulas, not the same. Okay, time for some. Okay, it's big brain time. V plus V naught is 2D over T. V minus V naught is AT. You guys have seen this in math class. It's called the difference of squares. A squared minus B squared is A plus B times A minus B. Right? A squared minus B squared. AB and BA cancel out. So, sorry, you can't see it. I wrote the same thing. A squared minus B squared is A plus B times A minus B. So we're doing the same thing. This is V plus V naught times V minus V naught when we multiply v plus v naught and v minus v naught, we're going to get v squared minus v naught squared. That's pretty obvious from just a mathematical point of view. What's the other side? It'll be a times t times 2d over t. The t's cancel. We'll get 2ad. This is a really useful formula because this equation doesn't have t. There's no time. Back in those like 1600 French video clay experiments, they didn't have stopwatches. There's no way they could measure the amount of time the ball took to sink into the clay because it's so fast. They would be using like sand, hourglass. That makes no sense. There was no way they could find the time. You don't need time. If you have a problem that doesn't give you the time and also doesn't ask for the time, use this formula. There's no time involved. You skip the whole step of finding time. I'll rearrange it because this is a little more straightforward. V squared equals V naught squared plus 2AD. So if you don't need time and don't have time, you're almost always going to use this formula. V squared equals V naught squared plus 2AD. And now it's clearly shown. If a ball hits the clay, I'll just use that example. If a car, let's say you're in a car and you're driving, and then a deer jumps in front of you and you hit the brakes as hard as possible, you care about your braking distance, how far the car goes before it's fully stopped. That's d, the braking distance. V naught is how fast you were going originally, so it's not 0, since you start out the problem driving a certain speed. What's v in this formula? Well, you start out driving, you hit the brakes, so you're stopping. V is 0. Your final speed is 0 meters per second. And in this problem, we're assuming your car's brakes, your car's machinery, the rubber and the tires, they give the car a constant acceleration. Not necessarily true, but it makes sense. And it's pretty close to true in real life. So A is constant. What happens if you take V naught and triple it? Will you triple D? No. If you double V naught, you'll quadruple D. If you triple V naught, you'll 9 times phi D. Whatever you do to V naught is squared, and that's what happens to D, the distance it takes to stop. So most of you guys probably don't drive, but here's a nice little chart. If you're going like 20 miles an hour, it'll take you 6 meters to realize you have to stop, and then 6 meters to actually stop your car. If you're going twice as fast at 40 miles an hour, it'll take you twice the time to realize you have to stop, to hit the brakes, your reaction time. But it won't take you the same 6 meters to stop your car. It won't take you twice as long to stop your car. It'll take you 4 times the distance. If you go from 20 miles an hour to 60 miles an hour, the distance the car moves before you react and press the brakes will be tripled. But this is what we care about. The distance the car moves while it's stopping. It goes from 6 meters to 55 meters. It goes, it's supposed to be 53, but rounding. It goes 9 times as much distance before it stops. It takes nearly twice as far to stop at 70 miles an hour as it does to stop at 50 miles an hour. 70 miles an hour is not double 50 miles an hour, but 70 miles an hour is about square root 2 times 50 miles an hour. So when you square the square root 2, that's how you get double the distance to stop at 70 miles an hour compared to 50. So a really useful skill, or a really useful thing to realize if you learn to drive, which you guys probably are not doing anytime soon. But yeah, if you are going twice as fast, it'll take you 2 squared 4 times as much distance to stop. So that's pretty good. That was like a little hint as to some things in the future. A lot of problems you'll see will have, oh, someone's driving down the road and a Komodo dragon jumps in front of the road. It takes them X time to realize, and then Y time to stop. How far did they go in the total time? You can't use this formula or the other I erased the formula or this formula to find the distance the car goes. You have to use both. All the formulas we're learning in this class right now assume A is constant. That's really important. Acceleration is constant. Of course, if A is changing, then they don't work. If you're in a car and you drive for like a second, then you press the brakes, you were not accelerating, and then later you were accelerating. So you can't just use one formula. You have to break the problem into two parts. Find out how far you went in the first part, then find out how far you went in the second part, and add them together, and that would be your total distance before you stop your car. So that's an example. You'll probably see some practice problems that involve something like that in the future. This would be a shorter video than my previous one. Yeah, everything's going great. I'm having a great life. Physics is pretty cool so far. Not much else to say. We'll spend some more time doing practice on these 2 units later. So now we learned this formula that doesn't have any time. It's really useful for finding your distance when you don't have time and you don't need time. While on the topic of reaction time, let's do a quick thought experiment. Just an experiment in our brains. So we figured out how to ignore time and solve this problem without time. How can you find a time without a stopwatch? So I was talking about reaction time. Reaction time is like how long it takes your brain to realize what's going on and then tell your body to do something, to like grab a meter stick. So this is like a little preview for our next lesson. Let's say you have a meter stick, but not a stopwatch. You guys may have seen this before, maybe you haven't. You can take the meter stick and kind of like hold it and then have someone else drop it. So someone's holding this meter stick. This is complicated. Someone's holding the meter stick and I'm not aware and they're just going to drop it and I have to catch it as soon as I can. If I'm really fast, I'll catch it right away. If I'm really slow, it'll fall, then I'll catch it. That's okay. How can we use the distance the meter stick fell to find the time it took me to catch it, my reaction time? So there's actually a way to measure your reaction time without a stopwatch. In fact, it doesn't really make sense to use a stopwatch. This makes much more sense. So how can we find time based on distance? How can we measure a human's reaction time without using any clocks, any stopwatches, anything like that, with only using a displacement of a meter stick? We'll see that answer to that question later. Bye.